Today we'll discuss delta functions, essentially an application of delta functions to differential equations. So first of all, let's discuss about rectangular signals. So the function which we call rectangular signal would be defined like this. R from rectangular from A to B, where A and B are two real numbers, non-negative, A is more than B, with height h. So at the top here we put the height of the rectangle of t. So we define this function to be 0 if t is less than a. Then it suddenly jumps to h if t is bigger than or equal to a and smaller than b, and drops back to 0 if t is greater than or equal to b. So if we have the graph, we get this will be a 0 until here, h from a to b, and back to 0 on the interval close b to infinity. So this will be the rectangular signal. That's the rectangle. So this is A, this is B, this is T. So this will be called R sub AB with height h of T. Rectangle from A to B with height h. Okay, so in order to find the Laplace transform, the best way is to represent the rectangle as a linear combination of unit step functions. So it's like I have a unit step function at A, so suddenly we jumps from A jumps from A to H, not from A to 1, but A to H, so to multiply by H, minus the unit step function at B, so to cancel everything which is after B. So what about this? H times U of T minus A minus U of T minus B. Look at this formula and see that it represents exactly this rectangular signal. So according to this formula, we have two jumps. One jump at A and another jump at B. So before A, nothing happened, no jump happened yet. So it will be 0. Between A and B, only this jump happened, so the whole parenthesis here becomes 1, so we get H. After B, both jumps already happened, and both jumps are 1 now. Unit step functions are 1, 1 minus 1 is 0, we get back to 0. So H times U of T minus A minus U of T minus B is the rectangle from A to B with height H. Then the Laplace transform of the rectangle R sub A, B, H of T is H times Laplace transform U of T minus A, e the minus A S over S, minus the Laplace transform of U of T minus B, e the minus B S over S. So this will be the Laplace transform of a rectangle. Okay, next, we'll move towards defining delta functions. Before defining delta functions, let me think about the process in which we consider tall and thin rectangles while preserving the area of the rectangles. So here's the main idea here. We'll consider tall and thin rectangles while preserving the area. So let's make it 1. So width, area 1. So this will be a rectangle between A and a plus a little bit, let's call it epsilon. So the rectangle is non-zero only between a and a plus epsilon, just for a thin amount of time, right? And within that thin amount of time, the value of the rectangular signal will be 1 over epsilon, so that the area will be the product of the two dimensions. One dimension is epsilon, and another dimension is 1 over epsilon. So the rectangle from a and a plus epsilon with height 1 over epsilon of t was the view on this. It's a and a plus epsilon here. So we get until here we get a 0. The ritual comes back to 0, then remains 0 to infinity. So if we want to put empty circles here, we put an empty circle here, circle here, empty circle here. We don't have to do this, but okay, for me, just let's do it one more time. So that's a rectangle with area 1, tall and thin. So the idea here is at the limit, when epsilon approaches 0, let's make it 0 plus, the rectangle becomes infinitely thin and infinitely tall. So we need to find the limit when epsilon approaches 0 plus of this r sub a plus epsilon with height 1 over epsilon of t. So what will be this limit? But we have a limit of functions here. And if we do limit point by point, we'll get a pretty much a paradoxical definition in which the function is 0 if t is not a, and infinite if t equals to a. But let's give more sense to this limit. So in order to give sense to the limit, we have to calculate the limit. So find the limit, or express the limit. Better express the limit as a distribution. Let me explain what does it mean. So let's call this limit, whatever it is, the delta function. So we want to understand how this delta function operates. To this purpose, we integrate both left-hand side and right-hand side multiplied by a test function. The test function is assumed to be have all the nice properties, infinitely many times differential. So let's try to integrate. So let's integrate the right-hand side times the unit step function. Integral from 0 to infinity, delta of t minus a times f of t is the unit step function, dt, should be equal to the limit when epsilon approaches 0 plus of integral from 0 to infinity rectangle r sub a and a plus epsilon height 1 over epsilon of t f of t dt. Now, if we manage to give formal sense to both left-hand side and right-hand side, we get a nice formal definition of delta function if we look at the left-hand side. But in order to give this to find a formal definition of this integral, which involves a new function, delta function at a, we have to evaluate the limit when epsilon approaches 0 plus of this integral when f of t is infinitely many times differentiable. So let's do it. Let me keep this and find the limit here. So we get limit when epsilon approaches 0 plus of integral from 0 to infinity r sub a and a plus epsilon with height 1 over epsilon of t f of t dt. This will be limit when epsilon approaches, so let me put it again here, equals to limit when epsilon approaches 0 plus. Because the rectangle is 0 to the left of a and to the right of a plus epsilon. This integral could be can be seen as an integral from a to a plus epsilon. And between a and a plus epsilon, the value of the rectangle is 1 over epsilon, which is a constant. Let's take the constant in front of the integral. So 1 over epsilon. Integral from a to a plus epsilon. There's the only interval when there's the interval over which the rectangle is non-zero. Integral from a to a plus epsilon, f of t dt. So maybe if we put in this form, integral over epsilon. Does it sound familiar? We have a limit of the form 0 over 0, 0 over 0. So when epsilon approaches 0, we get integral from a to a of f of t dt. That's a 0 over 0. So in these cases, we apply L'Hopital, right? And the limit will be limit when epsilon approaches 0 plus f of a plus epsilon over 1. Because f is assumed to be infinite many times differentiable, it is continuous, and this limit will be just f of a. So the right limit after our work until now, this will be f of a. So this is the conclusion of this work. So now this gives us a formal definition of the delta function as a distribution. So the delta function as a distribution operates in this way. So delta function delta of t minus k as a distribution. So it will be a functional. So let's call this delta of t minus a like a box. Delta of t minus a. That's an input slash output box. It receives as an input a test function f of t and produces as an output the value of the function at a. And in the form of an integral, the integral form of this picture is integral from 0 to infinity delta of f of t equals f of t delta of t minus a dt equals to f of a. Okay. For example, let's see. Integral from 0 to infinity. Let's see, sinus of t and delta of t minus pi over 2 dt. So this will be sinus of pi over 2. So the value of the function of pi over 2 is 1. Example 2 will be the most important for our purposes. Let's calculate the Laplace transform of the delta function. Laplace transform of delta of t minus a. Okay, so let's see. So Laplace transform of delta of t minus a is integral from 0 to infinity. Just use the classical definition of Laplace transform. E to the minus s t delta of t minus a dt. And again, we input the input function is this one. The output function is the value of the function at a. So e to the minus as. So you got a very important formula, Laplace transform. So delta function can be visualized like a shock at the moment a. And again, like we discussed before, it can be the interpretation with the limit of a sequence of rectangles which are thinner and thinner, while taller and taller, while maintaining the total area, a constant area 1. Right? This delta of t minus a. So let me write again the result of our discussion here up to now. Laplace transform of delta of t minus a equals to e to the minus as. And again, delta of t minus a is the limit of a sequence of thin and tall rectangles with total area, with area 1, right? If we want, for example, 2 delta of t minus a, what will be this? What should we consider for this? A limit of a sequence of thin and tall rectangles, but with total area 2. So this involves they're like thin and tall rectangles with area 2. So we have here rectangles between a and a plus epsilon, and then the height will be 2 over epsilon, so that the total area of these rectangles will be 2. So at the limit, when epsilon approaches 0 plus, in the sense of the distribution theory, this will be 2 delta of t minus a. So in this way, we can understand that there are shocks. So instantaneous, the shock is a sudden blow. So shocks can have different intensities. So like we have different multiples of the delta function. So 2 delta of t minus a is the limit of a sequence of rectangles, even thinner and thinner, taller and taller, but maintaining an area 2. Okay. Now let's discuss differential equations. Actually, we'll discuss when we restrict ourselves to oscillators and delta functions. So oscillators and delta functions. So let's consider the following initial value problem. X second plus x equals to, let's make it 3 times delta of t minus pi over 2. And x of 0 equals to 0, and x prime of 0 equals to 1. So that's an oscillator which starts like a, so this is like external influence. External influence could be force, could be current, depending on which context, in which context we apply this differential equation. And without this external influence will be x second plus x will be 0, and x of 0 is 0, and x prime of 0 will be 1. So what will be without external influence or force? We have x second plus x equals to 0, and x of 0 equals to 0, x prime of 0 equals to 1. That will be a sine t. So in this case, we get x of t will be sine t, because sine t at 0 is 0, and its derivative, which is cos t at 0, is 1. So a base of solution for this linear homogeneous constant coefficients is cos t and sine t. So the solution of this equation without external influence will be just sine t. So without this external influence, the oscillator will evolve always like a sine t forever. But now we have to bring in this action, sudden action, an impulse, if you want, or a shock received by the oscillator in the positive direction at the bottom in pi over 2. Okay, so let's see. Let's solve this initial value problem. So let's declare our intent to use the Laplace transforms. X of t transforms into big X of s, small x prime into sx, and small x second into s squared capital X minus 1, because of this transforms of derivatives. And the delta of t minus pi over 2 will be transformed into e to the power minus pi over 2 s just e to the power minus pi over 2s. Okay, so let's try to use this as a dictionary to convert the differential equation into S space. So we'll get this one will imply S squared big X minus 1 plus big X equals to 3 e to the power minus pi over 2 times S. Let's keep all x's on the left, so x times S squared plus 1 equals to 1 plus 3 e to the power minus pi over 2 times S. And then we get x, capital X equals to 1 over S squared plus 1 plus 3 times 1 over S squared plus 1 e to the minus pi over 2 times S. Okay, so this is basically the solution of differential equation, but encrypted. So encrypted in the sense that it's not in a T space, but it's in the S space. So what we need to do is to decrypt and find the real solution of the differential equation. Okay, so let me erase this work and keep this. I want to keep this one. So let me put it here. X equals to 1 over S squared plus 1 plus 3 times 1 over S squared plus 1 to show how we do it formally. That's e to the power minus pi over 2s. Let's take the inverse transform. By linearity, the inverse transform of the linear combination is the linear combination of the inverses. So this term is transformed back into sine t. Sine t is what would have happened without any external influence. So without this external influence, the oscillator will be ruled forever like a sine t. Now, this one is still a sine t, but because of e to the minus pi over 2s, we have what we discussed before, delay. By using a delay, because of delay result, this transforms back into u of t minus pi over 2 times sinus. That's a sinus, but the delay will be u of t minus pi over 2 to make sure that it's 0 before pi over 2. And then the translation to the right of sine t will be sinus of quantity t minus pi over 2. So put it together. More x of t equals to sine t from here plus 3 times u of t minus pi over 2. Now let's look a little bit of trigonometry. Sinus of quantity t minus pi over 2, sine t cos pi over 2 minus cos t sine pi over, minus cos t sine pi over 2. So times minus cos t. Okay, so now let's write down the solution. So x of t, in a reduced form, x of t would be sine t plus 3 u of t minus pi over 2, which I put a minus in front because of this minus cos t here, cos t. Okay, so that's the solution by formula, but it's better for us to discuss amplitudes to represent a diagram of this solution over a real number line. So until pi over 2, we got a jump here, and this jump did not happen yet. So we'll get, this will be 0, so we'll get sine t. So that's what will happen if the oscillator will go forever without any external influence. But then the shock comes here in the positive x-axis, and the formula starting with pi over 2 will be sine t minus 3 cos t, because the unit step function becomes 1 at this moment. So we can, if you look at this diagram, we can x of t is sine t if t is more than pi over 2, And then sine t minus 3 cos t if t is greater than or equal to pi over 2. What's the amplitude here? Until pi over 2, the amplitude of oscillator is 1. After pi over 2, the amplitude of a combination of sine and cosine is the square root of the sum of the squares of the coefficients of sine and cosine, the square root of 10. So the oscillator increases the amplitude when it receives a shock with intensity 3 in the positive direction. So let's try to explain why such increase. Well, such increase, let me better see a picture here. The picture will be, without external influence, the oscillator will evolve like a sine. But exactly the moment pi over 2, we have a shock of intensity 3. So in the positive x-axis. Then this causes the amplitude of the oscillator to jump from 1 to square root of 10. So starting from with pi over 2, the oscillator evolves according to a stricted sine function with amplitude square root of 10. So it's square root of 10 times sinus of t minus phase t. Okay, so let's try to discuss other examples in which the, let's say, oscillator receives more than one shock. Let's see another imaginary problem. X second plus x equals to delta of t minus 2 pi. Okay, plus 3 times delta of t minus 4 pi. X of 0 equals to 0. X prime of 0 equals to 1. Okay, so x of 0, x of t transforms into big X of s. So we declare our intent of using a Laplace transform. X prime into sx, x second into s squared x minus 1. And then the free term, delta of t minus 2 pi minus plus 3 delta of t minus 4 pi transforms into e to the power minus 2 pi s plus 3 e to the minus 4 pi s. Okay, so now let's translate the differential equation from the t space to s space. So we get s squared x minus 1 plus big X equals to e to the power minus 2 pi s plus 3 e to the power minus 4 pi s. So x will be what? Let's try to, now that we got our objective achieved, so let me erase the work. Then we get, from this equation, we solve for x. X will be, so keep those to the left, move minus 1 from left to right, and then solve for x. So x will be 1 over x squared plus 1 plus 1 over x squared plus 1 e to the power minus 2 pi s plus 3 times 1 over x squared plus 1 e to the power minus 4 pi s. So this will be the solution of the differential equation, but in an encrypted form, in that it's in the S space. So let's find small x of t. Find the inverse transform. We get small sinus of t, of course. This will be, okay, we can do it directly. So this will, okay, let's try doing roughly. This will be sin t again, but together with e to the minus 2 pi s, that's a delay. So plus u of t minus 2 pi sinus of t minus 2 pi. and shift combined with 0 to the left of 2 pi. That's a delay of the signal. Plus 3 times u of t minus 4 pi times sinus, because of this, sinus of t minus 4 pi. So that's x of t. Okay, let me write it down on top here. So x of t, the solution will be x of t will be sine t plus u of t minus 2 pi. Sinus of t minus 2 pi is the same as sine t because of the periodicity of the sinus, plus the 3 u of t minus 4 pi. And the same, sinus of quantity t minus 4 pi is still sine t because of the periodicity of the sinus. Here the solution in a slightly simplified form, but to see best, we just do such a diagram. That's a 0, that's a 2 pi, that's a 4 pi. Between 0 and 2 pi, it's sine t. No jump happened yet for sine t. And that will be the formula if the external influence will be absent. Right? Between 2 pi and 4 pi, the first jump already happened. The second jump didn't happen yet. So what we get here? 2 sine t. After 4 pi, both jumps happened. So both unit step functions are now 1. So we get sine t plus 3 sine t, we get 5 sine t. So sine t between 0 and 2 pi, 2 sine t between 2 pi and 4 pi, and 5 sine t between 4 pi and infinity. So let's see a graph here. Okay, so anyways, let's try to be smaller here. Between 0 and 2 pi, we get sine t. Between 2 pi and 4 pi, and put here 4 pi, 2 pi, 4 pi. Right? Between 2 pi and 4 pi, we get a double amplitude. Like this. And then, so this is a double amplitude. 2 here, minus 2 here. Now, between 4 pi and infinity, amplitude increases by a factor of 5. We make it 5 here. Then it will evolve forever with amplitude of 5. So, amplitude 1 here, amplitude 2 between 2 pi and 4 pi, and in this region, amplitude is 5. So let's try to explain why this happens in terms of the shocks received by oscillator. So the oscillator starts as a sinus. Right? X of 0 is 0, sinus of 0 is 0, cosine of 0 is 1, so it starts like a sinus. It will evolve like a sinus forever if it weren't for the external influence. Now, at this moment, it receives a shock of intensity 1, which causes the amplitude to become 2, right? At this moment, receives a bigger shock of intensity 3, and those two shocks are exactly when the particle was moving in the positive direction, so that the particle is eagerly absorbs the shock, which causes the increase in the amplitude. It will be different if the shock will be applied in the negative direction. So we discuss in the next problem this. But because the particle moves at any moment, there's 2 pi here, there's 4 pi here. At each of these two moments, the shocks, instantaneous shocks, delta functions applied to the oscillator at those moments is in the direction of the movement of the particle. So the particle really absorbs well the shock, which leads to the increase in the amplitude. Okay, so basically this kind of ideas can lead us to solve differential equations with delta function without only with visuals. So let me try to do one concrete example, both with the by solving by using the theory and just by using the intuition. So what about this? What about x second plus x equals to delta of t minus 2 pi. That's not 2 pi, delta of t minus pi. Look at this. X of 0 is 0, x prime of 0 equals to 1. Okay, so I'll not repeat, so let me do again write again what we will get. So we get a squared x minus 1, the transform by x second, plus x equals to e to the power minus pi s. So x will be 1 over a squared plus 1 plus 1 over a squared plus 1 e to the minus pi s. And that means x will be sine t plus, here is this is a sine t, this transforms back into a sine t, but that indicates a delay. So we have to shift with pi to the right, but on the left of pi we have a 0, so u of t minus pi times sinus of what will be t minus pi. Okay, so what will be this one? Sine t cos pi minus cos t and sine pi. Sine t cos pi is minus sine t. Sine pi is 0. So, so this will be small x of t. Again, small x of t turns out to be sine t we get minus u of t minus pi times sine t. Okay, so what we have, let's resort to our diagram between 0 and pi. We get a sine t. After pi, this shock happened, so this now is 1, the unit step function is 1. So what we get here, sine t minus sine t equals 0. So the solution of this oscillator will be like this. So before pi is sinus, after pi is 0. And again, it's very intuitive, because normally it will evolve forever as a sinus, but because of this shock, what happens? So it evolves forever as a sinus, right? But exactly when the particle was moving into the negative direction, it receives a shock which kind of matches the energy of the particle, matches the strength of the movement of the particle in the negative direction. So this shock will be in the positive direction. At this moment, everything will cancel. So the signal will die. So we get a 0 signal from this moment. We can play with this idea. So what about, so we'll get this solution right away, just we look at the meaning of the problem. So what about if we change the problem with the following, x second plus x equals to 2 delta of t minus pi. What will happen? Just do it without any theory, just by understanding the meaning of this. So normally it's an oscillator. Without external influence, it will evolve forever as a sinus, right? Right. But right at the moment pi, it receives a shock in the positive direction. So at the moment pi, oscillator was moving in the negative direction. But the shock that it receives at the moment pi, we put it pi. At the moment pi is double and it's in a positive direction. So imagine that half of this shock will put the particle to rest, and the other half of the shock causes the particle to start moving in the positive direction, exactly like a sinus type function. It's a shift of the sinus anyway. So the graph of the solution of differential equation will be like this. Because of this big shock, the oscillator will reverse direction, so we get something like this. Whatever. Now we can do a lot of ideas. So this of course easy because the points at which the shocks are applied are very nice values for which easy to calculate to figure out everything. But that's a good idea to which conveys the meaning of these shocks or delta flux.